Hello, everybody. Today we're going to talk about our new unit, charge and force. And today's topic is static charge and the structure of the atom. Now, you know what static charge is, or static electricity. That would be what we see here. For example, you touch a doorknob and you get zapped. You take off a winter jacket or your fleece and you hear the crackle. And then maybe you touch someone and you shock them, or you're walking across the carpet and then you touch a doorknob and you get zapped. Well, that's been going on for a very long time. In fact, the ancient Greeks were the first one to really talk about it, and they noticed that things like amber, when they wore them as jewelry and they rubbed on fur, would crackle. They also noticed that glass jewelry on silk, which they imported from China, that would also crackle and spark, and they saw weird things, such as forces moving these objects once they were charged. They didn't know quite what was going on, but they called this um, electros, which comes from the Greek word for amber. So amber on fur was an electric force. Years later, people started to really understand this. They would call it an electric fluid, they would call it all sorts of things. And one of the greats in the field was Benjamin Franklin. What he did was that famous key experiment that you have no doubt heard about or read about, where he discovered that a key flown on a kite during a thunderstorm actually started crackling with static electricity. So he proved that lightning was actually electrical. That could have killed him, by the way. Don't do that. But he also then was able to prove that you could protect yourself from it by a simple device, which was a metal spike, iron spike usually, that connected down from your roof to the ground. We call this a lightning rod. And one of the reasons he became such a celebrated scientist, as well as one of our founding fathers and such, was because the lightning rod stopped lightning from hitting buildings. It doesn't actually hit the lightning rod at all, which I'll demonstrate later in the course, but it prevents lightning from hitting anything or from generating or targeting the building, which prevented so many house fires. I'm not sure if there's a good estimate of it, but given that multiple cities had burned down because lightning struck somewhere in the city, started a fire, and then the fire spread out of control, he's undoubtedly saved millions of lives, possibly billions at this point. So, pretty impressive invention. Anyway, he codified and explained a whole bunch of the electrical stuff. And so a whole bunch of stuff that we've got now comes from him and the people working around his time. So one of the things that he found out, which we're going to be looking at, is that there are two types of charges. We call them positive and negative. And Franklin was the one to say which one was negative and which one was positive. He knew that one moved and one was still. And so he kind of figured out that much, but which one was which, he didn't know. So he just named them as best he could. The other thing he knew and that we know is that when we bring charges together, so we try to take two charged objects and push them together, they'll do one of two things. They'll attract, which means they pull towards each other, just like magnets, or they repel. They're pushing towards each other, but we just can't get them to touch. And that would be a repulsive force. You can't get them to touch, they push away. And it turns out that like charges, that is, the two charges are the same, they're both positive or both negative, like charges repel. Whereas opposite charges, one positive and one negative, attract. And we're going to show this as well in class. The question is, though, okay, so we've got these charges, but where do they come from? What creates this charge? How does something get charged? All that stuff. So let's begin with that. Charge comes from the structure of the atom, which was not well understood at all during Franklin's time. They had the concept from the Greeks, atomos, indivisible, but what an atom was, they didn't, they were still way off of. And so you can see an atom here on the left side of the screen. So in the center, that light green nucleus is where the protons, the red neutrons and the blue protons live. All right. And around the outside in green are the electron orbits or orbitals, where the light green electrons live. And you can tell there's different symbols for these electrons and protons and neutrons, and those are over on the right. The electron is E negative, E minus, because electrons are negative. The protons are P plus because the protons bear the positive charge. And the neutrons are N0 or no because they have no charge at all. The nucleus is where the mass of the atom is located, so it's made of protons and neutrons. And the orbitals are where the electrons are located, and they're mostly empty. Electrons are absolutely tiny. Now, to give you an idea of the scale we're talking about, suppose I took a simple atom and made the nucleus the size of about a golf ball, okay? And I went over to a football field, and right in the center of the 50-yard line, I put that golf ball. Where would the electrons be? And the answer is they would be around the stands. They would not be on the field. They'd be out in the stands. They would be very far away. And they would be so tiny you wouldn't be able to see them. Furthermore, the rest of the atom, everywhere where an electron was not, would be empty space. So the simplest hydrogen atom, which is one proton and one electron, would mean the electron is somewhere in the stands and the whole field is empty except for this one golf ball sized proton in the middle. Most of the atom is completely empty, and the mass of the atom is all concentrated in that nucleus. Now, you may be catching a logical inconsistency in here, right? Because the nucleus is where all the positive charge is, but we said like charges repel. So how on earth do the protons all stay together in one spot when they're pushing each other away? This was something people didn't understand until they realized that's the job of the neutron. Once you start getting more than one proton in the nucleus, like helium, which has two protons, you start needing neutrons because they help neutralize that force and they prevent the whole thing from flying apart. And the more protons you add, the bigger the nucleus gets, the more neutrons you need. And eventually, you've added so many protons that you just can't keep the thing together. And that's responsible for the nucleus falling apart. That's instability and radioactivity. And eventually, radiation and nuclear power all comes from that. But from the fact that the protons really don't play very well together unless there are a lot of neutrons there to keep them going and keep them together. All right, so the repulsion is real. Meanwhile, of course, the electrons are being pulled inwards towards those protons, but they never actually touch because they're moving so fast and so randomly. That's a whole topic of its own. Quantum mechanics is really cool, but you can get more into that a little bit in chemistry. So, okay, we know that there's this atom and it's got these charges in it, but how does rubbing things together actually do the charging? And well, we call this particular way of charging by friction. And you take two uncharged insulators, they rub together, and then one of them takes charge, transfers charge off of the other, which means that one of them now has more positive charge and the other has more negative. And these two objects wind up with opposite charges. You are separating the charge, right? Two neutral objects, one becomes positive, one becomes negative. All right. Now, the other thing to note about that is that means charge is like energy and momentum. Charge is conserved. All right. Conservation of charge, which you want to write down, means that you don't gain or lose electrons or protons in any of these reactions, in any of these charging or uncharging things. The electrons just get moved around, right? You're just moving the charges. The same number exists before as exist after. They're just arranged differently. Okay? So I mentioned that insulators were rubbing together. So what's an insulator? Insulators and conductors are two different things. They do the opposite thing. An insulator is a lot of different things like wood, plastic, pure water, and I mean pure, has to be absolutely 100% pure. Ceramics like, like cups and mugs and whatever, cloth, skin, hair, wood, all those things, they are insulators. And that means that charge cannot flow freely through them. And so when you charge the outside of them, that charge sticks. Meanwhile, conductors are things like metals and salt water, where the charge flows freely through them. So they can transmit shocks very easily. They can do what's called grounding, where you transmit the charge from a person into the ground or from an object into the ground. By the way, this is why we take copper wires, because the wires are metal, and surround them with plastic, because the plastic makes sure that the charge only goes through the copper, and when you touch that wire, it doesn't go through you, which is very important, because of course, if a charge goes into my finger, how does it get out? It gets out by running down my arm and across my heart, and now I have a heart attack. This can be very dangerous, so be very careful about touching bare wires. Another thing to note is that if you're outside in a thunderstorm, dirty water, salt water, any kind of dirt in water makes it more conductive. And so if you're in a lake or an ocean, or you're near a big metal pole, being outside during a thunderstorm is fairly dangerous, because if lightning strikes the big metal pole or strikes you, or strikes near you, so the salt water or dirty water will conduct the charge right into you. So if you're at the beach, any kind, lake, ocean, whatever, and you see a thunderstorm in the distance, out of the water. You can die otherwise. On the other hand, if you are in a thunderstorm, get into a car or a building, right? Don't touch like conductive metals. There have been cases where like someone was taking a shower and the water and the lightning just came right through their window. But for the most part, you'll be pretty safe. And if you're in a car, you've got those nice insulating rubber tires, which means that lightning will never strike a car as long as those tires are insulating and preventing lightning from flowing through and getting to the ground. All right. So lightning is very protective. Or sorry, rubber is very protective from lightning. All right. So remember your conductors and insulators. The thing about rubbing an insulator on something is that once you charge it, the charge sticks there. All right. So which charge flows? Well, that comes from the charge of the atom. We know that there's positive, we know that there's negative, and the structure of the atom is going to tell us which is which. All right. If you look at the atom, you'll notice that the electrons are on the outside, and there's mostly empty space there. So the protons and neutrons in the nucleus never get close to the outside, so they can't jump from atom to atom. The electrons are all the way on the outside, which means electrons are the only charge that moves. Any question you're asked about which charge is moving or what's moving, it's always the negative charge. It's always the electrons. Now, there are some formalisms that Ben Franklin put in place that say the positive charge moves. I'm going to ignore those for now, but just understand, whenever charge moves, it's really electrons moving. All right? Protons and neutrons can never move unless you do a nuclear reaction like radioactive decay, nuclear bombs, nuclear power plants. Those are the only things that move protons and neutrons. Everything else, all of chemistry, is electrons. Chemical reactions, etc., all electrons. So, okay, we get that electrons move, but who's positive and who's negative? We're rubbing our insulators on each other. Who's positive? Who's negative? Turns out there are rules. All right? There's something called the triboelectric series, which basically says, hey, these guys are the big electron stealers. They'll take electrons, and these guys don't mind giving it up. Okay, so that's why, for example, air is one of the biggest electron losers out there. That's why thunder is, because when air rubs on each other, the humid air and the dry air will then exchange electrons. And when the electrons try to get back to, equalize the charge, we call that lightning. Okay, so if you look here, and you might want to write some of this down, but basically, rabbit fur is a big electron loser. So is glass. Okay, human hair and fur are big electron losers. And so then you get all the way down to things like rubber copper and nickel and polyester and a lot of plastics tend to be big electron gainers. All right. Whereas steel and cotton, they tend to be more neutral. They don't really pick up or lose charge, although steel will happily conduct it. So basically, the big electron gainers, nickel and copper, love them. They love gaining electrons, although they're conductors. So generally speaking, if you do that, they will conduct the electrons away from each other as much as they can. And we'll go into that more in a later lecture. So rubbing plastic on fur, well, you look at it and you take a look down, and the plastics are on the electron gainers. So the fur is going to become positive because it loses electrons and it has more plus left. The plastic becomes negative because it gains negative charge. It gains electrons. All right. So the negative moves off of the fur and onto the plastic. All right. Whereas, for example, if I were going to take a rubber balloon, I could rub it on fur and the balloon would then take electrons. If I were going to take some silk and rub the balloon on that, the silk would lose electrons and become more positive. All right. So the total number, remember, stays the same. It's just distributed differently. And I'm going to include a PDF of a triboelectric series in the electricity folder. All right. Just right there before the first lesson, I think. All right. So when these objects are rubbed together, take a look at them, place your bet. You can go back if you need to and take a look at the series. Silk and glass. Silk becomes what? Glass becomes what? All right, we've entered our answers in the Edpuzzle. Excellent. So the silk is going to become negative. It's going to, even though it is an electron loser, the glass is an even bigger electron loser. So the glass will actually end up donating and it will become positive, whereas the silk will end up taking it, so it'll become negative. All right, what about these two? Rubber balloon and human hair. We do that, right? You've all had a rubber balloon rubbed on hair or seen it or done it. So Edpuzzle, right? Okay, exactly. So the rubber balloon is going to become negative because it's a taker. It's going to take all that charge and the hair is going to become positive. Right, guys, that's it for this one. And I will see you on the next one. Have a nice day.